Okay, good morning. Welcome everybody. Welcome to my presentation on how classical coding theory meets the quantum world, where I will show you how we can use classical techniques from error correcting codes, coding theory in a quantum setting. First of all, let me acknowledge my PhD students, current and former, who contributed quite a lot to these presentations. We have Jonas, Adam, Kari and Sissi. And the financing, this work was financed mostly by the European Union and the German Ministry of Research and Education. So let me give you a brief outline of what I will talk about in this presentation. After briefly introducing the background and setting the context, I will talk how we can use coding in a post-quantum cryptography setting, so how to realize post-quantum cryptography, how we can use coding for quantum key distribution, and last but not least, how coding is an indispensable technique for building quantum computers, so for quantum computing. So we all know error correcting codes or coding theory is an indispensable technique in communication systems. We use it in mobile communications, we use it in satellite communications, in fiber-based communications, but also in storage systems. We all know that these systems cannot provide reliable data transmission without the use of coding, which helps us reduce residual errors and push the error rate down to acceptable limits. In storage devices, this is especially important because you don't want to lose access to your data. And we also all know QR codes, and QR codes we can put a little logo here and there, and this will help us for recovering the data in the QR code. Now, in the quantum world, we also need coding. And this is what this talk is about. So in the last couple of years, we have seen a rapid development of quantum computers. And we now are in a situation where first quantum computers may, with a little star, may beat conventional setups. We're not fully there yet, but we're in a good way. However, the quantum circuits we implement, they are heavily affected by noise. And this is why we need some kind of error correction on a circuit level. Now imagine we have a quantum computer. Once we have a quantum computer, we can run Shor's algorithm and we challenge current cryptography schemes. So we also need a workaround on current cryptography schemes. And this is what this talk is about. So what is a block code and what is an error correcting code? So we start with a very formal definition of a block code. And you can see here the formal definition of a block code. A block code of length n, cardinality m, is first of all defined over some finite field, typically. And it's a collection of m elements from the field f to the power n. So we can see here the definition. So the code essentially is nothing else as a set. And this set contains vectors, and we have vectors x1, x2, up to x capital M. They are vectors of length n with elements from the field. Each of those vectors is what we call a code word, and the parameter n is the block length or the dimension of the code. And we choose the number of code words such that m is equal to the cardinality of the finite field to some power k, and k is the information length of the code. So it means we can map k symbols of our vector of k symbols from the finite field to a unique code word of our code. Very important parameter of the code is the rate, and the rate of the code is essentially divided as k over n, or the logarithm of number of code words divided by n, and it's a matter meaning of how much redundancy the code adds to the system. We constrain ourselves mostly to linear codes. Code is called a linear code if the code words make up a linear subspace of f2 to the power n. And the following, we restrict ourselves mostly to binary code, where the finite field under consideration is the binary field, so 0 and 1. If we have a linear code, the code words can be defined using the null space of a parity check matrix. So we have a parity check matrix H, and we define the code words as the null space of this parity check matrix, which means the code words are given as all the vectors x of length n from the field, such that h times x transpose is equal to 0. So we search essentially for all the solutions that fulfill the system of equations set up by the parity check matrix. Linear codes are essentially practical codes because we can show that we can achieve Shannon's capacity using a linear code. Great. Linear codes are also easy to implement. Many simplifications exist for implementing encoding, but also decoding of linear codes. And we have one extremely popular example of a linear block code, which is an LDPC code or low density parity check code. It's used in 5G, it's used in Wi-Fi, it's used in many communication systems. And low density parity check codes are defined by a sparse parity check matrix H and are among the most popular codes that exist. We can represent the code by its tenor graph, and a tenor graph is just a different way to visualize this system of equation that defines the code. So here we have a code and assume this is the parity check matrix of the code. So we have a parity check matrix, and the parity check matrix defines 3 equations that the code words need to fulfill. So the code or the parity check matrix has a length of 7. So we have 7 columns, and this means our vectors x have 7 entries. So we have code word consists of 7 bits in this case, and we visualize these 7 bits by 7 nodes in our tenor graph. These are called the variable nodes. Now we connect them to check nodes, and we connect them such that we visualize the parity check equations. So we have a first parity check, which is C1, and C1 depends on the first row of the parity check matrix. The first row of the parity check matrix over here essentially says that x1 plus x2 plus x3 plus x5 must be equal to 0. So what we do is we connect C1, the first equation, to x1, x2, x3 and x5. Then we keep on doing this. We repeat this for the second row. We have C2. So C2 essentially says second row of the parity check matrix, x1 plus x2 plus x4 plus x6 must be equal to 0. And we connect C2 to x1, x2, x4 and x6. And finally C3 says that x1 plus x3 plus x4 plus x7 must be equal to 0. So this is the tenor graph of a code. And the tenor graph is an important representation because it leads us to an extremely efficient decoder, which is the belief propagation decoder or BP decoder, and it has many other names. It's also called as message passing decoder, some product decoder, etc. And you can think of this decoder as a decoder operating in the tenor graph, and each of those nodes, they are small computers computing messages and passing these messages along the edges in the graph, and by that they help gaining better beliefs on the originally transmitted bits. So think of these nodes in the tenor graph as small computing engines. They compute messages and they pass these messages back and forth. The operations are extremely simple. If we look at these variable nodes, the circular nodes in the tenor graph, they essentially perform computations in a rather specific way, which is beyond the scope of this talk. But think of these as carrying out additions based on the messages coming from the check nodes, from the square nodes. And below you have the final equation. The check nodes, on the other hand, they perform a different operation, which looks a little bit more difficult or involved, but in the end of the day, it's also very easy. So think of these check nodes, the square nodes, small computers. They get messages from the variable nodes and they calculate this equation, which involves hyperbolic tangents and products. And so it looks a little bit involved, but hardware designers have come up with very clever solutions on how to implement this on digital hardware and on analog hardware. So these are essentially the operations that you do, and then you repeat those couple of iterations iteratively until you have reached some kind of convergence. Okay, so how can we now use codes for post-quantum cryptography? First of all, what is post-quantum cryptography? Well, we all know that cryptography is necessary to guarantee security and privacy in our data and in communication systems, and cryptography is a tremendously old technique. Cryptography has been invented more than 2000 years ago by Caesar and others. And if you want to really dive into it, please visit cryptool.org. You can play around with different approaches, and there are excellent textbooks and popular books on cryptography that I highly recommend. Now, in recent years, state-of-the-art cryptography schemes, they are heavily challenged by quantum computers. And it may be that once we have a quantum computer, current cryptography schemes are not secure anymore. And this is why we need new cryptography schemes, and their error-correcting codes come to the rescue. So, current public key cryptography, as we have it, is vulnerable to quantum computers. So, the way it typically works is we have Alice and Bob, they would like to communicate with each other. And what they do is they agree on a cryptographic key, and they use this key to set up an encrypted communication. And then we have an eavesdropper, Eve, who is interested in the content of the messages. So Eve is the attacker and the nasty person, and Eve would like to get the communication. So we're going to see in this talk two alternatives that are not yet challenged by a quantum computer. The first one is an algorithmic method called post-quantum cryptography, and the second one is a method called quantum key distribution. Let's dive into the first method, the algorithmic method. So, first of all, to define how this method works, we need to define what is a crypto system. A crypto system is like an encoder. It's very similar, a striking similarity to encoders and decoders that we use in communications. And a crypto system is essentially a system that has a set of messages M, which we call the plaintext space. It has a set of keys K, which we call the key space. It has a set of ciphertext, which we call the ciphertext space. And this is like the information messages, the encoded messages, and we use a key to encode. So then we have an encryption function. The encryption function E is a function E that depends on some key K. So it is parameterized by a key K, and it maps essentially a message from the plaintext space to the ciphertext space. So it's a mapping from M to C using a key. The decryption function does the inverse. It's also parameterized by some key K, and it goes from the ciphertext space to the message space. Now we want perfect reconstruction. We don't have noise, we want perfect reconstruction, and we get perfect reconstruction if for any key that we have, there exists another key K prime, such that if we encode the message with key K and we decrypt it with key K prime, we recover the original message. So D of K prime of E of K of M is equal to M. K and K prime, they don't need to be the same. They can be the same, but they don't need to be the same. And we say that a crypto system is secure if an attacker cannot deduce the content of the message from the ciphertext E during a time in which the message is relevant. So we may be able to store the message and in 10 years decrypt it. That depends a little bit on the level of security that you want to guarantee. So what is a symmetric and asymmetric crypto system? We mostly consider asymmetric crypto system. Symmetric crypto system, both parties have the same key and use the same key for encryption and decryption. In an asymmetric or public key crypto system, we have two keys. We have a public key, kPublic, which is on a central repository. You can find it on the internet, it is shared with everybody, it is completely public, and it's used to encrypt data. So if somebody would like to send you a message, he looks up your public key, he encrypts the message using your public key, and he gives it to you. And then you have a private key, and this is the one that belongs to you. This is, you put it in your locker, you put it in your safe, and you don't share it with anybody. So this is secret. And this key used for decrypting the data. So this is what is called a public key crypto system, and it has many advantages because you can put these public keys anywhere. You don't need to walk around exchanging a secret key. The secret key belongs to you, you don't share it. Okay, so what are the properties of the public key crypto system? If you encode the message with the public key and you decrypt it with the secret key, you recover the original message M. The functions encryption and decryption, they should be able to be implemented very easily. And most importantly, you should not be able to find the secret key from the public key or only using an immense computational effort. And this is the underlying scheme that is used, for instance, in RSA. And RSA is public key crypto system that you probably all have used, that we use essentially every day in our lives. And it's challenged by quantum computer because the public key and the secret key, they belong on the fact that it's very hard to factor a large number into two prime factors, and you can only do this by trying many times unless you have a quantum computer, because there you can run a Shor's algorithm which does that in acceptable time. So how can we implement such an asymmetric crypto system using coding? And the idea of this is the McAlice crypto system, and it is a scheme that has been derived or presented in the 1950s, more than 70 years ago. And it's very easy, but it has not received widespread attention until the recent year when the RSA scheme is under attack. So what is the idea of the McAlice crypto system? The idea of the McAlice crypto system is that encoding a linear code is very, very easy. However, decoding a code, if you only have the parity check matrix, is hard. Unless we know a simple decoder, which cannot be deducted from the parity check matrix. So I gave you this belief propagation decoder. That decoder only works for parity check matrices that are sparse, where you have very few connections in the graph. The more connections you have, the worse the performance gets, and you are not able to run it anymore. Other decoders, they have similar issues. So the decoder only works if you have a very specific code, and if you know what kind of code you have, then you can use it. So what is the idea of the McAlice crypto system? The idea is you take your plain text, you encode it with an error correcting code, and you add intentional errors. So you add intentional errors here. This is your ciphertext. Then your decryption is essentially a decoder that removes the intentional errors and will give you the plain text. Now you may argue that if we add errors, this will not help because we can only correct a fraction of errors. So most of the data will still be valid or uncorrected. So we also need some helper functions to disguise or to obfuscate the code word. And this is what the McAlice crypto system does. This is the general idea, and let's go to the details now. So the encoder is public. Everybody can encode and encrypt. Encoding is simple. The decoder is secret. So we have a code where we know we have a very efficient decoder that can correct T errors. We keep it secret. Everybody else must use a general decoder, for instance, syndrome decoding or a very bad decoding algorithm. And if you want to do this well, this is an NP-hard problem. And it's infeasible unless the number of errors you introduce is very, very small. And then you just make it larger. What you need to do is you need to scramble the parity check matrix so that you cannot deduce the decoder from the code. And this is a very efficient scheme. It's secure so far, and it's secure because coding theory, thanks to communications, is a very well-studied field where we have a lot of underlying mathematical tools and analysis. And so far, we don't know any quantum scheme that can crack the algorithm. We could use Grover's algorithm, but it will not be able to sufficiently reduce the complexity. So what are some of the research challenges in the McAlice scheme? The key size in the McAlice scheme is significantly larger than your traditional RSA. You're talking about keys that are megabytes of size large. So exchanging keys may become a communication bottleneck. Also, the encrypted message is larger than the original message, which is not the case in traditional RSA. There, the encrypted message has the same size as the original message, more or less the same size. Then means we need to find schemes with small key sizes, meaning compressible keys. We need to find high-rate schemes that do not increase the encrypted message size. And we need to find schemes that are safe against attacks. Possible candidates are the McAlice scheme based on copper codes. Other candidates are the BIKE scheme based on medium density parity check codes. You can see some information on bikesuit.org. And currently, the NIST is standardizing post-quantum cryptography schemes. You can see the link here, which I also put in the description. And there you can find more details about this standardization. And the McAlice scheme and the BIKE scheme, they are among the candidates in the fourth round of the coding scheme. Okay, so we have seen how coding can help us in deriving new post-quantum cryptography schemes. So now let's move on quantum key distribution. So we saw that in order to prevent Eve from eavesdropping the communication, we used an algorithmic method, which is post-quantum cryptography. But we can also use a physical method, which is quantum key distribution, which utilizes quantum physical effects to guarantee reliable and secure communication. And this is based on a quantum channel that Alice and Bob set up to transmit so-called quantum states. And we're going to see how we can set up such a system and how we can use error correcting codes to make it secure. So the first step that Alice and Bob do is they transmit something called a quantum state. And quantum state sounds like a very mystical object, like something that you need to carry in a cryostat. It's not true. A quantum state essentially is a modulated symbol, a modulated waveform at an extremely low signal-to-noise ratio. That's it. So Alice transmits quantum states to Bob. Bob measures these quantum states. Then you throw away a certain amount of these quantum states. You estimate the transmission parameters, etc. And then you use something called a key reconciliation, where you use error correcting codes to make sure that Alice and Bob actually have the same key. And then there is another step called privacy amplification, where you make sure that the two parties have a key and that an eavesdropper cannot leak any information from this key. So how does this key reconciliation, we're now jumping into this key reconciliation block, how does that work in detail? And how do we use error correcting codes? So here is the key reconciliation. It looks very complicated, but it's essentially very easy. The first thing you start with is with a random number generator. We have this quantum random number generator that produces true random numbers. We take these random numbers and we encode them by an error correcting code. Now we have a code word of our error correcting code, C. Now what we are doing is we modulate this code word onto the received quantum states. So here we transmit the quantum states X and Y, these are the quantum states. So we transmit those and now we modulate the code word onto the quantum states. We transmit this back to Alice and Alice knows what quantum states she has transmitted. So what Alice does is she divides the received modulated states by the transmitted states to remove the influence of these quantum states. And then she uses a decoder to decode the code word. And that's the key reconciliation. And then you have some protocol overhead to make sure that actually Alice and Bob have the same key. So first Alice needs to check that she actually has a code word, and then they introduce some hashing functions to make sure that they actually have the same code word. And that's how the key reconciliation works. Now this poses a lot of challenges for error correcting codes. Essentially, we have error correction that we perform on these quantum states, and we need coding schemes for very, very low signal-to-noise ratios. It's totally different from communications, where we typically operate on high signal-to-noise ratios. We usually want to transmit a lot of data. We improve our devices to get better signal-to-noise ratio. Here we have very, very low signal-to-noise ratio, minus 20 dB. And we need capacity approaching codes, because otherwise the system will not be secure. Multi-edge type LDPC codes turned out to be a very good candidate for this task. And the problem is, however, the optimization is really difficult because we have a very high dimensionality. So we have proposed, actually my former PhD student Kadir has proposed a solution that drastically reduces the dimensionality of this optimization problem, and these are called type-based protograph codes. So we can see how these codes perform compared to reference schemes, and for this we carry out Monte Carlo simulations. So here we have the error rate as a function of the signal-to-noise ratio, and we compare our proposed codes with reference codes, the AR3A and AR4A codes that are also used for space communications. And we start with a code of rate 1/5, and we see that our scheme has more or less the same performance as the ARXA code, and they perform within half a dB of capacity. If we reduce the rate, we actually start to outperform the reference code, and we still perform close to capacity. For rate 1/8, we get even better, and for rate 1/10, there was no ARXA code anymore, and we took another code from the literature. Then we also see that for rate 1/10, we outperform the reference code, and we are within less than half a dB from capacity. If we further decrease the code rate, and we typically need code rates in the order of 1/50 to 1/100. Again, for code rate of 1/50, we outperform the reference, and for code rate 1/100 with the proposed method, we also outperform the reference. So what are the challenges that we have? We could think of, we have a good code design, everything is nice. However, the challenges are we need to operate very, very close to capacity. If we are further away from capacity with our operating point, we essentially leak too much information to the eavesdropper, to a potential eavesdropper. So we need to operate very, very close at capacity. Now, the typical approximations we now do in the decoder, Remember, we have this hyperbolic tangent operation in the decoder that is usually approximated using a simple minimum. You go to logarithmic domain and you can use a variant of the algorithm called the min-sum algorithm. Unfortunately, at very low SNRs, this min-sum algorithm doesn't work well anymore. So here you can see simulation result. We compare the min-sum with the sum product algorithm, and we see a difference of roughly 5 dB. So with the min-sum decoder, we have challenges, so we need to find new simplified decoders. We also need very large block lengths in order to get close to capacity, and this may also be challenging for hardware implementation. If you build a hardware, you need a lot of memory inside your decoding circuit. And you need high precision of the messages, because at low SNRs you have a lot of dynamics in your messages. So decoding algorithms, to summarize, from communications, they don't work anymore in quantum key distribution, or in particular in continuous variable quantum key distribution. And for this scheme, we proposed new adaptive scaling decoders. We proposed new decoders in the logarithmic or the double logarithmic domain that can drastically reduce the bit width. There is another effect that happens in quantum key distribution compared to communications. In communications, we have the Schmalen limit that tells us that the error probability goes to 0 if and only if the rate of our code is below the achievable rate of the channel or the mutual information of the channel, which we call IAB. And typically, if you think about a communication system based on a fiber optic cable, the signal to noise ratio increases or decreases with the distance. So if you increase the distance, the channel becomes worse because you have losses in the optical fiber, you have dispersion, etc. And this means the achievable rate will also go down over the distance. So what happens is that the rate goes down, or the achievable rate of the channel goes down if we increase the distance. And if you operate a code at rate R for short enough distances, the rate is below the achievable rate and you can have an error probability going to 0, and in the other cases error probability will go to 1. Now in quantum key distribution it's different, because the metric is not the error probability anymore, but the metric is the so-called secret key rate. So how much key material you can transmit per second. And the secret key rate is given by this equation. So what does the secret key rate say? The secret key rate says that it's 1 minus the error probability of the decoder times some stuff, which is the rate of the code, or beta times the mutual information of the channel, minus the Holevo bound on the information that you leak to Eve. So this term cannot become negative. If this term becomes negative, the secret key rate is negative. You cannot transmit any key material. So the rate of your code must be larger than the information that you leak to Eve. So you cannot have an arbitrary low code rate, but the rate of your code must be large enough so that you don't leak information to Eve. And still, you need to have an error probability that is below 1. Otherwise, secret key rate is also going to 0. And this means that typically you have reconciliation with a fixed code only works in a certain regime. You have a regime when the rate is below the mutual information. This is where decoding is possible. But if you have a too good channel, the Holevo bound becomes too large. You would leak too much information to Eve, and the secret key rate is not possible anymore. So you have a very, very narrow range of operation where you can actually operate your code. And this is why we don't want to build systems that operate at one specific point, but we need adaptivity. And this is why we proposed an adaptive key reconciliation. And here you can see the theoretical limit of the secret key rate as a function of the transmission distance of our optical fiber. And we see that we have secret key rates in order of 0.1 bits per transmitted symbol to 10 to the power minus 3 bits per transmitted symbol. And this is because you need to throw away a lot of quantum states that are useless or that you need for error correction. This is the effective secret key rate. This is the theoretical limit that we can get. And with a single code, so we design a code of rate 1/10, we can operate at a distance of 50 kilometers. And we can get a relatively good secret key rate only at a distance of 50 kilometers. And if we just deviate a little bit from 50 kilometers, it doesn't work anymore. Same if we take a code of rate 1/100, we can operate at a transmission distance of a little bit above 100 kilometers, but then it doesn't work anymore. Okay, so what can we do? We can introduce an adaptive key reconciliation scheme, and with adaptive key reconciliation schemes, which are very similar to the rate adaptivity that we use, for instance, in 5G, we can operate very, very closely to the theoretical limit. So we can follow the theoretical limit very, very closely. There is a small gap here, but that is not practically relevant. Okay, so this summarizes our efforts that we did for quantum key distribution. So we have now seen how we can use coding for post-quantum cryptography. We can use coding for quantum key distribution. Now, if we want to build a quantum computer, we also need coding. So how can we use coding for building a quantum computer? This is what we do now. We start with very, very quick tour into quantum information processing and then go to quantum error correction. So, what is the motivation to use error correction in a quantum computer? Well, if you build a quantum computer and quantum systems, they are not coherent. They decohere. And this is because the quantum systems, they constantly interact with the environment, and the quantum information decays over the time if we don't protect the information. And the threshold theorem says that a quantum computer that has a physical error rate below a certain threshold, we can suppress this logical error rates by using quantum error correction, and we can get arbitrary low levels. So arbitrary low error levels on a logical qubit level, quantum level, can be achieved if we use quantum error correction. Okay, so worldwide tour quantum information processing, the main unit that we have is what we call a qubit. And for a qubit, we use this bracket notation. Now this is a cat, and we have this cat phi is essentially alpha times cat 0 plus alpha times cat 1. So 0 and 1, they are called the basis states. And you can think of these as just vectors, 0, 1 and 1, 0. So cat 0 is just a vector called 0, 1, 0, and cat 1 is a vector with 0, 1. So just the two basis vectors. Now alpha and beta, they are complex numbers. So alpha and beta complex numbers such that alpha squared plus beta squared is equal to 1. And that means that the state is essentially a vector, a two-dimensional complex vector with an extra constraint. That is a qubit. So think of a qubit as a vector with complex coordinates with some normalization constraint. And typically we talk about a superposition because we superpose the two basis states. So it's a mixture or superposition of the basis states 0 and 1, which are the unit vectors. And we essentially can use any two states as basis states as long as they are orthogonal. And these bases, they are essential for measurement. So if we measure a quantum state or qubit, then this qubit here that we have over here, so this one, it will be 0 with probability alpha squared, and it will be 1 with probability beta squared. So we cannot measure alpha and beta. It's a superposition. But once we measure, so we put a measurement device, once we measure, we get a 0 with probability alpha squared, and we get a 1 with probability beta squared. Now we can also see why we have this condition that alpha squared plus beta squared must be equal to 1, because they act essentially as probabilities. All right, so we can define multiple qubits. A multiple qubit basis is the tensor product of a single qubit basis. So we have the multi-qubit basis 0, 0, and it's a tensor product of basis 0 with basis 0 itself. And we know that this cat 0 is a vector 1, 0. So it's a unit vector 1, 0. And we take the Kronecker product with 1, 0, and then we get 1, 0, 0, 0. So we get a 4-dimensional basis vector. Same Kronecker product 0, 1, we get 0, 1, 0, 0, and we can take all 4 combinations of zeros and ones with the Kronecker products, and you see we get basis vector of dimension 4. So these new products, they form the basis states for 2 qubits, and the vectors are now lengths 2 to the power 2 equals 4. And if we combine n qubits, the vector length is 2 to the power n, so we have 2 to the power n basis states. And this is this exponential power of a quantum computer. You have n qubits and you have this exponential power, so you can use n qubits to represent 2 to the power n basis states and essentially represent any combination of these basis states, and upon measurement you fall back to one possibility. These states that we have seen, they are called separable states because they can be written as a product of 2 states. We have something called entangled states, and they cannot be written as a tensor product of simple states. For instance, this Einstein-Podolsky-Rosen or EPR state is written here, so it's 0, 0 plus 1, 1. These are the 2 basis vectors. So we have 2 qubits that are entangled. You have, so you can think of this as being 0, 0 with probability 1/2 or 1, 1 with probability 1/2. So you have 2 qubits, they are entangled. If you measure them, both qubits are either 0 with probability 1/2 or both qubits are either 1 with probability 1/2. And this is what is called entanglement. It means you can generate these 2 entangled qubits, you can move 1 qubit somewhere else. Once you measure them, they will have the same value because they are entangled. They are either both 0 or they are both 1. And if you measure one of those qubits, you directly determine the state of the other qubit. And this is the main technique and tool that we use for quantum error correction. So, of course, if you want to build a computer, you need gates. So we have our typical digital computer, we have AND or XOR NOT gates. And similarly, we have gates in a quantum computer. It's not so easy in a quantum computer because we are a little bit restricted on what gates we can have. And the gates essentially need to be defined by a unitary matrix. So if we have a gate that acts on an n qubit state, we have a gate, or the gate is defined by a 2 power n by 2 power n unitary matrix U. And essentially the gate operation means we multiply our state, our vector, with the unitary matrix U. So what gates do we have? There are many gates that we can think of, essentially all unitary matrices, but we give the most important ones, which are the Pauli gates. Pauli gates are the identity gate, which does nothing. So it's just the identity matrix. We have the Pauli X gate, which defines a rotation of 180 degrees along the x-axis, which is a bit flip. So the x-axis, if you think of a representation of the qubit in a space, you can think of an x-axis. So if you apply x to the 0 state, it will become a 1 state. If you apply x to the 1 state, it will become a 0 state. That's the Pauli X gate. So essentially just a bit flip. The Pauli Z gate is a rotation along the other axis. So if you apply Z to the 0 state, it will stay the 0 state. If you apply Z to the 1 state, it will become a -1 state. So it's essentially a phase flip. Here you don't have any phase, no flip. If you have a phase, you flip the phase. The Pauli Y gate is a combination of X and Z. So the 0 will become a -1 and the 1 will become a 0. Nice thing about the Pauli gates is essentially that any unitary transform can be written as a linear combination of the Pauli gates. Pauli operator is also known as Pauli noise, and these are a common error model in quantum computers. So the Pauli errors or the Pauli gates, they act as noise on the quantum states, and you can have errors from the Pauli group, which is the identity matrix, the X matrix, plus minus the X, plus minus Y, plus minus Z, and they can be multiplied with the imaginary unit I. So we can also have a flip by an imaginary unit. Now if you have a Pauli operator on multiple qubits, we just use the tensor product of the Pauli matrices. So if we have a if X is acting on the first qubit, Z is acting on the second qubit, we generate the tensor product of X and Z, and we get this matrix which acts on the 2 qubits, which is again unitary matrix. And we can write the Pauli operator then as just XZ, and this is another operator acting on 6 qubits. So we have the first qubits are not affected, we have the identity mapping, then 2 qubits are affected by the Z error, 1 is affected by X error, and the last, the 6th qubit, is not affected at all because we have identity matrix. One important gate is the C0 gate. C0 stands for controlled NOT gate, and is essentially a controlled flip. So we have 2 inputs. We have 2 qubits as inputs to the C0 gate, and one of the inputs acts as a control gate. So we have phi1 state. If this phi1 state is equal to 1, phi2 is flipped, and otherwise phi1 is not flipped. So phi1 is mapped to phi1, and phi2 is mapped to phi1 plus phi2. And this is a tool that can be used, the C0 gate can be used to build entanglement or to realize entanglement. So here is the C0 circuit. We have phi1 that is just passed through, and phi1 controls what happens to phi2. So we have phi1 plus phi2 acting. Okay, so this was everything you need on quantum information processing. Now we move, how can we build quantum error correcting codes? There are some complications which prevent us from using classical error correcting codes in this setting. The first one is the no cloning theorem. The no cloning theorem says it's not possible to clone or to build a copy of a quantum state. So we cannot use a traditional repetition code. We cannot just go ahead and just clone some states. This will not work. The second issue is that once we measuring destroys the superposition. So we cannot peek into the code word and see, we may need to correct something. Measurement destroys superposition. And then we have not a single error type, but we have multiple error types. We have continuous errors. So they're all very complicated, and there has been a lot of work building up, starting with very simple codes, building up on a whole framework that we're going to see in a couple of seconds. So one of the first error correcting codes in a quantum setting was the 3-qubit code, and the 3-qubit code essentially corrects any bit flip error on 3 qubits. The 3-qubit code is analogous to a classical repetition code. So here we have our circuit. What we have over here in the circuit is we start with a quantum state. We have superposition of A and B. So we have our state. And we do a C0 with 0 as second input. So we do 2 C0s. So we have an entangled state A times 0, 0, 0 plus B times 1, 1, 1. So we use these 2 C0 gates to generate an 3 entangled qubits. This code can essentially correct with a correction circuit, which is beyond the scope of this quick presentation, can essentially correct one bit flip error, so one Pauli X error. Now the nice thing about quantum error correcting codes is that if we can correct an error A and B, we can correct any linear combination of these errors A and B. And this is a result that still puzzles me to this day because it's very counterintuitive, but it means we only need to care about correcting discrete Pauli errors, because every error can be written as a superposition of Pauli error, as a linear combination of Pauli errors. So what is the idea of the error correction? The error correction is, the idea is that we take these ancilla qubits, which are these extra qubits that we introduced, we measure those and we collapse the error to one of the Pauli errors, which we can then correct. And this is the main idea that is behind the framework of what we call stabilizer codes. So a stabilizer code is among the most popular quantum coding construction, and the stabilizer code with parameters n and k, very similar to classical code, so length n, k information qubits, and we use these double brackets to denote that they are quantum error correcting codes. Stabilizer code is derived from an additive code over a Galois field GF4. You can think of a Galois field GF4 as an extension field of the binary numbers, which contains 0, 1. So we have 4 elements, 0, 1, omega and omega bar. And we have operations, addition and multiplication, that work in the same way as for real numbers. Okay, so the stabilizer code is defined by a check matrix S from this GF4 and essentially defines a system of equations that defines the code words. And we use a mapping that the elements of GF4, they define the Pauli errors. So 0 is mapped to identity, 1 is mapped to Pauli X error, omega is mapped to Pauli Z error, omega bar to Pauli Y error. And the so-called CSS, Kelderbank-Shorstein construction, says that you take 2 classical random codes, HX and HZ, and you construct a check matrix where you multiply HX, which is a binary code. So you take a binary code HX, you multiply it with omega, you take a binary code HZ, you multiply it with omega bar, and you get the check matrix. So this is how you can construct a stabilizer code. Now we have some condition. You cannot just take any HX and any HZ. Doesn't work. You need some condition. The condition is that HX times HZ transpose must be equal to 0. So these matrices must be kind of orthogonal. And what that means is that the code CZ, so this is the code defined by the parity check matrix HZ, is a subcode of HX, or the dual code, so the dual code of CZ is a subcode of CX. If that is the case, we get a quantum CSS code which has dimension k equals n minus rank hx minus rank hz, and we have a minimum distance that depends on the minimum distance of the individual codes. And this immediately brings us to LDPC codes, because we can define hx and hz to be LDPC codes. We have sparse parity check matrices and we get a sparse check matrix. And these quantum LDPC codes are nowadays very, very important quantum error correcting codes. How does the coding scheme work? So you have a logical quantum state phi L, and you encode it using your quantum LDPC codes. On the channel, there is an error E that acts on the state. So you have this state phi and you have an error E that acts on the channel. We saw we cannot measure the code rate directly because it would destroy the superposition. But what we can do is we can measure a syndrome. And so we measure something called a syndrome, and then we use this syndrome in a syndrome decoder to get an estimate of our quantum error E hat. And then we just undo the effect of the quantum error on the noisy code rate. So we multiply E hat by E times phi. This is how a coding scheme in a quantum computer works. We typically assume the depolarizing channel, which means the Pauli errors X, Y, and Z, they occur with the same probability. And essentially the syndrome decoder is a belief propagation decoder that acts on the syndrome using the check matrix S to find an error which yields the same syndrome. Question that we have: is belief propagation a good choice for decoding quantum LDPC codes? Theoretically, we can use belief propagation decoding of a quaternary linear code. That would work, but we'll find that performance is not so good. So the reason is that if we look at the check matrix of the code, we find that the tenor graph that is associated with this check matrix contains a lot of short cycles of length 4. And from classical modern coding theory, we know that short cycles of length 4 are very detrimental for the performance of the belief propagation decoder. So belief propagation does not work well with short cycles of length 4. And here you can see an example. So here we have the physical error rate on the x-axis, we have the frame rate on the y-axis. We see the performance of uncoded cases, the solid line. We see the performance of the BP decoder, and only for low error rates it's actually better than uncoded. For high error rates, uncoded would even be better than the BP decoder. And we have some decoders using graph theory that perform much better. Now the question is, can we use the BP decoder, which is very well researched? We have very, very efficient hardware for building the BP decoder, low latency, good hardware, etc. Can we use it for decoding quantum LDPC codes? This is the research question that we have. The answer is partly we can, and I will show you one possible solution to this problem. So problem statement is: short cycles of length 4 are unavoidable in the tenor graph of quantum LDPC codes. And if we look at this example, so we have the check matrix with hx and hz, and by construction, hx times hz transpose must be equal to 0. So it means for the rows of hx, they must have an even number of overlapping ones with any row of hz. So here we have two examples. Here we have the first example, we have 0 overlapping ones. 0 is an even number, so that would work. But if we have 2 overlapping ones, this is, so this 4 ones, they will form a cycle of length 4 in the parity check matrix, and this is very, very detrimental for decoding. So can we construct a code that has no cycles? Yes, we can, but these codes have very, very poor distance properties, so we cannot correct any errors with such a code that has no cycles of no short cycles. So what are some existing solutions? One solution is to decode the X and Z errors separately using the 2 separate codes. This is the binary BP2 decoding. So we can construct quantum LDPC codes where the different graphs of hx and hz are good for BP decoding individually, but they are suboptimal for the depolarizing channel because we have also Y errors. And we can optimize the BP decoder for codes with detrimental structures. We can use all kind of techniques, post-processing techniques. We can use machine learning And we have own previous work on this. You can see the bottom reference where we use machine learning decoder. Problem with these approaches, they are not universal. They are designed for one specific code. Complexity becomes larger and possibly also the latency becomes larger. This is why we propose a new approach, which we call CAML. And the question is, can we construct codes with 4 cycles which are not harmful for decoding? And this is what we do with CAML. So we start with the condition or the constraint that our traditional codes need to have. We know that hx times hz transpose must be equal to 0. Now the CAML ansatz is to take a detour and reconstruct codes where h1 times h2 transpose is equal to 1. So just the opposite. The constraint is not fulfilled with this code. But then we set hx to be h1 followed by a single column with 1s, hz to be h2. Remember, h1 and h2 fulfill this condition. So hz is h2 with a single column of 1s. And then if we multiply hx by hz, we get 0 as required. So this is the CAML ansatz. So this ensures essentially that we have no 4 cycles in the tenor graph associated with the code as h1 and h2. So we have an S prime, which is the codes belong to h1 and h2, and S is then given by S prime followed by a column of scaled 1s. So what that means is that in this part of the parity check matrix, we have no cycles of length 4, and all cycles of length 4 that we have, they are concentrated and assembled in this last column. So the nice thing about this is that this constraint has been studied quite a lot in classical coding theory, so we can use existing approaches like finite geometry codes to construct very good codes that fulfill this condition number 1. So how do we deal with the cycles of length 4 that are assembled in this last column? What do we do? Therefore, we use ensemble decoding. So we use 4 parallel paths, and what we do is we say, okay, if the last qubit here is problematic, we just try out all the possibilities for the last qubit. So we try all the 4 possibilities, 0, 1, omega and omega bar for the last qubit, and then we use BP decoding. And then we get 4 estimates of the code word, of the error. In this case, it's the error, it's not the code word. So we get 4 estimates. We get E0, E1, E2, and E3. And then we just pick the most likely error. And then we get the error E hat. So each part of this ensemble decoder gets a hard guess of the last column. And essentially it means we virtually remove the cycle in the BP decoder. And each path is responsible for one specific type of error pattern with the last column. And this is together our CAML scheme, which stands for cycle assembling and mitigating ensemble decoder. And this has been presented very, very recently at ESIT, and I will also put a link to the video of the conference presentation where you can find more details on CAML. So here are some results of the CAML scheme. So the dashed curve you see here, there are a lot of curves, but let me quickly walk you through it. So we have the error rate as a function of the depolarizing probability of the channel. The dashed curve is a reference code. It's a 416 hypergraph product code, which means you take 16 logical qubits and you map them to 400 physical qubits. Now, with our codes, we get this performance, so we get a significant improvement, and even with this code Q1, which is a 1512 code, where we take 12 logical qubits and we map it to 50 physical qubits. So factor of 4 less than the hypergraph product code. And we get slightly better performance. And with the code Q5, where we take 36 qubits and we map them to 362 physical qubits, we significantly outperform the hypergraph product code. So with the same number of physical qubits, roughly 400, we can map 36 logical qubits instead of 16 and get much, much better performance. So this is really a great step forward for building possible quantum codes. You may ask why you have 362, why not 400? This is because with the construction that we have, we are not 100% free yet to choose the size of the codes. We have some constraints that we need to take care of. Here's another example where with Euclidean geometry codes, again we have a reference code which is the 800-400 bicycle code. This is this curve, and we see that with our code E5, where we have a similar rate, we get significantly better performance, and with code E4, where we have a slightly lower rate, we get we can also outperform the code. So we can also outperform many existing codes using the camel construction, and for more details, please take a look at the video. So what is the reason for the performance improvement? We take a quick look at the code E4 from the previous slide, and we start by investigating a couple of decoders. So here we have a couple of decoders. We have the BP2 decoder, which is if you decode HX and HZ separately. And if you have the BP4 decoder, you get this performance. So for this code, the BP4 is already better on the depolarizing channel than the separate decoder, which makes sense because in the separate you cannot take care of the Y errors. If you extend the BP2 decoder with the post-processing, in this regime you have an improvement, but in this regime you don't have an improvement. So now if you use a BP2 decoder with a gene-aided decoding, or BP4 decoder with gene-aided decoding, which means we have our code and we have this problem on the very last position. We don't know the last position. If you now have a genie that tells you the value of the last position, then you can see that you can get rid of this error flaw. Then the error rate drops. And this is because this error flaw is due to the short cycles of length 4. And if you use a gene-aided decoder, the performance drops. And now if you use Camel, essentially you get the performance of the gene-aided decoder because you try all the possibilities for the last position. You still don't know which was the correct one, but then by picking the most likely error, you will find the correct one. This is the reason for performance improvement of the Camel scheme. Okay, so let me conclude the presentation. So we saw that coding theory is an indispensable tool in the quantum world. Coding theory helps us to design secure encryption schemes, to securely exchange quantum keys, but also helps us build a quantum computer. And if you really want to get into quantum information processing, quantum computation, I very, very highly recommend the book by Nielsen and Chuang. And it has an in-depth treatment of quantum computing, quantum information processing, and also a very good detailed chapter on quantum error correction. So with this, let me also take the opportunity to advertise the ITG SEC 2025 conference, which is a conference that we are organizing locally in Karlsruhe at KIT, which is the International ITG Conference on Systems, Communications and Coding. So it has a big track on coding theory, and it will happen from March 10 to 13/25 in Karlsruhe in Germany. Deadline for paper submission is September 27, 2024. So you have some time to submit a paper if you read this and watch this on time. So with this, we're at the end of the talk. If you have any question, please use the comment section of the YouTube and ask questions. And again, I take the opportunity to acknowledge funding from the European Research Council and from the German Ministry of Education and Research, BMBF. Thank you very much for listening, for having the time. If you have any questions, drop us an email, use the comment section. Thank you very much.